Welcome to KINE2253, Motor Development Across the Lifespan. This lecture will discuss the 14th chapter of Lifespan Motor Development, the 7th edition, by Haywood and Getchell. This lecture will provide supplementary examples and explanations to help provide a deeper understanding of the book chapter. In this lecture, students will learn about historical and contemporary perspectives on the relationship between perception and action, describe how perceptual processes change as a function of self-produced locomotion and other skills like goal-directed arm movements. They will understand the interdependence of perceptual, cognitive, and action or motor systems. And lastly, they will describe how perception and action interact to help us control our balance and posture. Let's begin by discussing how action is related to perception. As we have discussed throughout this course, different developmental systems are interrelated. Cognitive, social, physical, and motor or action development influence each other. Movement is necessary for the coupling and tuning of perception and movement. Let's take, for example, learning to catch a pop fly in baseball. When we first learn to catch a pop fly, we may be inaccurate in our movements towards the ball and positioning ourselves in the right place to catch the ball, because we have poor depth and spatial perception. But as we practice and move, we become better at judging the height and speed of the ball. And as we become better at judging the height and speed of the ball, we become better at planning and timing our movements to successfully catch a pop fly. At that point, our movements and perceptual judgments are coupled and fine-tuned to each other. Although we now understand that motor, perceptual, and cognitive development are interrelated, historically these systems have been studied separately. Sensory perception was considered to be a precursor of movement and cognition. For example, the basic components of the letter D and B are the same. There's a rounded part and then there's a straight part, but the arrangement is different. If a child could not distinguish this difference in orientation and arrangement, they may have difficulties with skills like reading. Researchers thought that if perceptual and motor problems could be identified using different assessments, and that children practice perceptual motor skills, that learning disabilities like dyslexia could be fixed. But there was little evidence that perceptual and motor programs reduced learning disabilities or improved other classroom skills. Jean Piaget, who was considered the father of developmental psychology, theorized that action and sensory development are actually interconnected at each stage of development. But during infancy, both action and perception are not well developed. Today, educators and therapists use perceptual motor activities to reinforce important concepts that are needed for academic skills. For example, tracking objects, playing with shapes, practicing eye-hand or eye-foot coordination, and learning about spatial directions and orientations. These skills help children develop necessary precursors for other motor and cognitive tasks in the classroom. Table 14.1 has a long list of the features of contemporary perceptual motor programs that can be used in the classroom for children with and without learning disabilities. Additional evidence for the relationship between perceptual, motor, and cognitive systems derives from neuroscience. In particular, brain-derived neurotrophic factor, or BDNF, is a chemical that is released in the brain that stimulates building and maintaining the nervous system. Exercise and motor tasks have been shown to increase the amount of BDNF in brain areas important for learning and memory and build connections between these important brain areas. These data are based on studies of animals that are put into cages with exercise wheels or put into play areas that facilitate motor skill development. And they find that these brain areas are larger and have more interconnections amongst other relevant brain areas. The results from these studies suggest that children would benefit from active learning instead of passive learning, where children sit quietly and listen to the teacher. Instead, they should interact with their environment and move through their environment as they're learning. Ecological views proposed by Gibson suggest that infants use their senses to perceive their environments and its properties before they can produce purposeful movements. But, as we saw in the last chapter, infants have poor sensory function, which limits the type and accuracy of their perceptions. Nonetheless, these perceptions help guide movements and exploration of the environment through infancy and early childhood. So, sensory perceptions improve actions, which in turn improve sensory perceptions. This process is called the perception action loop. In other words, perceptions of the environment may spark new motor skills to emerge. These new motor skills provide new sensory perceptions, which may spark further exploration of the environment. Some of the most important studies that help provide support for the importance of movement and the development of perceptual skills is a study by Held and KINE. In this first study, 2 kittens were placed in a merry-go-round and tied together such that one kitten could walk and the other was passively moved within a gondola. Although both kittens were exposed to the same visual environment and as such could have the same sensory experiences, the kitten that actively moved and gained movement experience in the environment was able to accurately judge depth and object movements. However, the kitten that was passively moved in the environment was not able to do these tasks. Therefore, self-produced movement or active exploration of the environment was necessary for the development of visual perception, and not necessarily vice versa. As we learned in Chapter 13, the development of depth perception was investigated using visual cliff studies, in which depth perception was developed as a function of locomotor experience like crawling or walking. To determine the impact of locomotor experience on perception, Bertenthal, Campos, and Barnett, and Kermoyan and Campos provided artificial locomotor experience to pre-walkers using a baby walker. Although these infants could not walk independently, the support from the baby walker enabled them to explore their environment and provided them with the same type of visual experiences as they would get if they were walking independently. As a result, compared to infants that were the same age but did not have access to this artificial locomotor experience, the infants in the baby walkers had better spatial perception, including height and depth perception. Lachman investigated infants' abilities to understand object properties, including spatial properties such as dimension, distances, and interactions between objects and their environment. Lachman found that reaching and grasping experience enabled infants to improve object and spatial perception and understand things like object properties. A similar study was conducted by Mackenzie and Bigelow, but this time the goal was walking around a barrier instead of reaching around a barrier, as in the Lachman studies. Mackenzie and Bigelow found that spatial perception increased with locomotor experience, such that infants with locomotor experience were able to determine the shortest path around a barrier better than those with less locomotor experience. The ability to match sensory perceptions with a set of possible actions was based on these studies and others by Gibson using the visual cliff or exploring sloped surfaces. For example, if the slope was too steep, the infant might not crawl down the slope head first. He or she might choose to turn around and crawl backwards leg first to prevent injury. This is only the case for infants with crawling experience. Ecological psychologists like Gibson suggested that what was first perceived by the infant is the affordances in the environment for movement. In other words, what types of movements are appropriate for a given environment and given the capacity of the individual performer. This match between the environment and the actions available in that environment are directly perceived and do not require in-depth analysis of object characteristics, but rather this is learned through experience moving in the environment. An example of the concept of affordances was discussed way back in Chapter 2. In this example, a step might be too tall for an infant to climb with an alternative stepping pattern. Infants might need to use a crawling pattern instead. However, a step is easy to climb using an alternative stepping pattern for a typically developing adult or child. The properties of the step itself don't change. The types of movements that are possible by the individual are very different because of the differences in size. This is an example of body scaling. Tool use is another example of matching perception and action. Infants use trial and error to explore the properties of tools and how they can be used in the environment. The affordances learned are not necessarily specific to each tool, but rather how any object can facilitate different types of actions in the environment. Self-generated arm movements, like reaching for and manipulating tools, provides opportunities for perceptual learning of these types of affordances. Affordances incorporate information about body scale. We discussed the concept of body scaling in Chapter 2. But as a reminder, body scaling is a person's size relative to the environment or objects in the environment. Obviously, body scaling changes over the lifespan with physical growth. Scaling of sports equipment and different aspects of the environment can enable people of different sizes to perform the same movements. For example, this basketball hoop is scaled to the height of the child so he can dunk the ball. The hoop can also be raised relative to the height of the child so he can shoot the ball. Now we'll talk about how perception and action help us to control our balance and our posture.